Buongiorno, my name is Hannu Lätti, I come from Valmet, and I'm going to show you now how can you use the kind of modern control methods for reducing your raw material costs and kind of squeeze everything out from your raw materials and not to waste them. Starting from the challenge. So the challenge typically is for many products that quality information, it has quite low frequency and it comes too late. Many of those key properties of especially board, they are the strength properties. And there are no reliable methods of measuring the strength online, so you are relying on laboratory measurements. Laboratory measurements are coming from every machine reel, so you get them once per hour or once per 40 minutes, depending on how often you get the jumbo roll out from the machine. But it's not very frequent. You got it, let's say, once per hour, and it comes also delayed. So when there is a turn-up, it takes 30-40 minutes before you get the result from the laboratory. So your strength information is very infrequent and delayed. So if you are facing the situation that your strength value is below your minimum level, when you get that information, you are already producing the next machine reel halfway. So this is the situation you don't want to face. Difficult questions. Do I have a recheck the whole machine reel or actually also the next one? You want to avoid it, and in typical way to avoid it can be seen from this figure, which needs some little bit explanation. So that shows you now the burst strength of a board with 10 different grades manufactured in the machine. And it shows the distribution of those strengths of these 10 grades. So each of the small black dot is one measurement from one machine reel. So this is a 1 year of data. And in 1 year of data, you can see that grade number 3, we have a burst strength from 325 up to 375, and the distribution of the machine reels are like this. So in order to avoid to hitting that minimum level, typically machines are running over quality. So the quality is higher than needed to avoid that one point that you are below and you face difficult situation. That's the challenge. If you would have more frequent information, you could run more closer to the minimum, but you don't with this laboratory method. The solution is that you can use the sensor data to create the model for these strength parameters, and then you can get the real-time information of that strength and not only the laboratory. And now, instead of having these small samples taken from top of the machine reel and measured in laboratory and get the result in delayed time, we take the sensor data from the machine and we are creating a model for those strength parameters. Or it doesn't need to be strength, it can be something else. Surface smoothness, it is not any way kind of limited to strength only, but the strength is typically the most critical one, so which cannot be measured online. So we create model, for example, in this example case, we have a model here for burst strength. Typically, you can create very nice model for the burst strength, explaining the burst very well by the usage of sensor parameters from the machine. In this example, the accuracy is roughly 95%. We have about 10 parameters in the model explaining and predicting the burst strength. And we can see here the blue graph is the actually laboratory measurement strength, and the red one is the prediction. They go very nicely hand in hand. So we have very accurate prediction. Now when we have this prediction, we can use it to calculate this strength estimation example once per minute. And now instead of having information from laboratory once per hour and delayed, now we can start example by projecting this prediction to machine operators. So now instead of having only laboratory measurement, operators can see a real-time prediction of that key strength parameter from the in this case we have a separate screen to project it to the operators. So operators can react faster because they can immediately see if there is some change in the strength, up or down. They can then accordingly adjust the process, increase the amount of starch, decrease the amount of starch, increase the amount of more expensive fiber material or decrease according to the strength situation. So they can run it kind of closer to the minimum because they have information every minute, not only just once per hour. So this system works in the way that we have a model running in the computer, in the automation system in the mill, and the model is calculating the prediction, and the prediction is projected to the operator who can see it and in real time can make control actions faster than based on the laboratory data. This is kind of the first step. Then, of course, as now we have a model, we can also take a step further and we can kind of skip this operator action. And we can start to control the process directly based on the model. This gives you even more savings because operator is not having time to only follow the prediction all the time. He has many tasks. He needs to do many things in the machine. He doesn't have time to look only this one parameter. But if we put automatic controller, it does not have anything better to do than only trying to optimize that strength level to be in the set point value. So this is kind of the way how you really get then the real benefits out when you automatize you close the loop. You make the closed loop strength control based on the model. I have two cases example cases that how this creates value for you, this solution. The first example is start shaving in a linerboard machine. So let's take now the example. We have now here 4 different grades in the linerboard machine, and we can see that in average they are running about 16 kilopascals burst strength over quality. So the distribution of this grade example is like this. The minimum is here, and the average value that they have is here. So there is a 16 unit difference in average between the minimum and the average level. Now, especially by cutting these high level points away, where we have a lot of over quality, by kind of having automatic control, cutting them away, narrowing the distribution, we can then bring this average to the new level. So we have a new average burst by using this advanced control method, closing the loop. And so let's now assume that in this case, let's assume we can reduce this overquality by 9 kilopascals. When we are using the model, we are knowing example in this case that this equals roughly to 4 kilos per ton of starch. So now by dropping this target lower, we can save 4 kilos per ton starch. And then it's of course is depending on the machine size and the price of the starch, that how much you save. But let's say that assuming now the high prices of starch at the moment hovering somewhere 500 euros per ton, we can see that in this kind of average size machine we could be easily achieving 600,000–700,000 savings per year by controlling this starch better. Another example case is a white line chipboard machine. Producing 3-layer product, white line chipboard machine. In this grade, the stiffness is the key parameter. That's the most interesting you want to get. And quite often, not all of these machines, but quite often many of these machines, they are applying CTMP to the mid layer in order to get enough thickness, enough stiffness to the product. And now in this example, we would have automatic control for that CTMP content. So again, similarly, we can see here that we have extra stiffness, in this case a lot. We have 2.2 millinewtons extra in CD directional stiffness. And by using automatic control, model-based advanced process controller, we could narrow down the distribution and drop our average level closer to minimum. And in this example, it's assumed that we would be cutting the over-quality by 1 millinewton. And again, not going to details that much, but we can utilize this model to estimate savings. So we know based on the model how much VCTMP affects to this stiffness level. So we can see that this 1 millinewton drop is actually equalizing CTMP content drop of 10 grams per square meter. And again, by knowing the price differences between the OCC material and the CTMP material, which is actually quite high, typically several hundreds of euros. Again, with, let's say, medium capacity machine with 300 tons per year, we are easily discussing saving amounts which are in millions. So, example here, the difference have been used 250 euros per ton between OCC and CTMP. You can save 2.5 million by running it more accurately, closer to minimum. I have one reference case, one mill where we have done this and already running for some years. Exactly the situation was here, like I showed to you. So there was a critical strength parameter, and typically it was much higher than the target window because of the safety factor. The operators play safe. And it's not only that they play safe, but because they have just information so rarely, it is not possible to run so accurately. There needs to be some safety margin. So in this case, before we sold this APC controller, we used their data and we simulated the results. So but because we can take the history data, we can run the simulation. We can kind of run the history data through that controller in order to see that what that controller would have been doing. Which is very easy and secure way to see that what kind of results we can reach. And in this case, we were easily seeing that the operators are running the set point much further away from the actual strength target. So the zero line is the strength target. Operator have safety factor, so it's higher strength than it should. And also the distribution is wider. So if we simulate that what is the control doing, if it would have been in charge, we can see it runs directly where we have a target, and also it's more narrower. So we simulated that we can save long fiber. In this machine, they use mechanical fiber and long fiber. And this long fiber, this craft is several hundreds of euros more expensive than the mechanical fiber. So we simulated that how much less long fiber they can use, and we were ending up at roughly 2 million. We started up this system 2 years back, and we have been achieving that 2 million. And also the very positive sign is that this control is basically always on, so operators are trusting it. They are always using it. It's always working well. So we reduced the variability of the strength 40%, and we were able to drop the amount of long fiber by running it more accurately in the target window and not so much over quality anymore. And actually, in this mill, the next step is that we are widening this. They are so happy with this system, and it's proving so well how it works that we are now extending this control for other quality parameters as well. So we are widening the system. How to start this kind of journey? It's actually quite easy. It's not need that you need to do all the way to the very end in one step. It's maybe a little bit small text, but it's showing to you that there is a kind of step-by-step approach how we would be going toward this kind of fully automatic control. And the first step is basically that we have a feasibility analysis. So we can take your data, batch load, 1 year of your data, machinery data, sensor data, and the laboratory data. And we can check that how good models we are able to create for that critical strength parameter that you have. And if we can see that, hey, we seem to be having good models for this case, then we can use those models also to simulate savings. So we can run that history data through that model and see that how much of raw materials, example, this system would have been saving if it would have been in charge. So it's kind of an easy way to start. This first step is not costing that much. And after that, you kind of have a good understanding if it's possible to create those models and start savings. And you can then, after we see that we have a model and we can simulate that there is a payback, then it's kind of up to decision that would the next step be operator guidance, like I showed that we are projecting the information to operators so that they can react faster, or whether it would be going directly to the closed loop control. So you can go directly as well, but you also, if you want to play a little bit safer, you can have this operator guidance phase first in order to kind of get everybody in the mill on board and the operators to kind of to create trust to the system. And only then, after there is a good understanding that it really works and operators are believing that the system is giving you credible advices, then you can go to the optimizer after that. That's what I wanted to tell you today. Thank you for your attention, and grazie.